So now that we know a little bit about waves, what we want to do is start talking about wave interactions. Superposition essentially is wave interactions. So let's say we have two waves sort of occupying the same place, maybe one like that, and another one, I don't know, like that, just something irregular. Doesn't really matter what the wave looks like. And so what superposition is if these things are both in the same place at the same time, well, how's that going to work? Because you have particles from this wave wanting to go up and down. Let's say it's a transverse wave, particles from this wave wanting to go up and down. They can't both do this wave and this wave at the same time, so what's the result? Well, the result is you just add the waves together at every point. So for example, the resulting wave at that point would be that length plus that distance, and that results in, maybe something up here. And so our wave might go like that. And then, here, this value's at 0, but the blue wave is not, and so it's going to be just whatever that value is, and so maybe it continues down like this, and so on and so forth throughout the whole wave, adding up the waves at each and every point. And so the result, you'd get a resulting wave from that. That act of adding together these waves at every point to see what results is what superposition is. So superposition is kind of the process of adding waves together. What happens during superposition is that you get what's called interference. So interference is really sort of the result of what happens when those two waves add together. We can have two types of interference. The first type is constructive, and looks something like this. So here's wave 1, here's wave 2. Notice they're kind of exactly the same wave. So if we had both of these exact waves, let's say going through air, if it's a sound wave at the same time, well, superposition says add up every point. So x plus x gives me twice x, so doubling the amplitude. Down here, negative x there. So everywhere, they're sort of adding together to increase the overall amplitude and intensity of that wave. The other type of interference we have is destructive. And during destructive interference, we get something like this. So here I have the two waves, again, same amplitudes, but this time exactly opposite. So if they're exactly opposite, let's say that's +1 and -1, that's going to be 0. +1, -1, that's going to be 0. At every point, they're exactly opposite of each other. So when you play those two waves together, they simply cancel each other out. Now, a very important point to think about here. If this wave is traveling this direction and that wave is traveling that direction, they just overlap for that moment in time. Only during that time that they overlap are they 0. That doesn't just kill the wave right there. So this wave, if it's going this way, will go this way, temporarily be 0 as they interact, and then continue on its way, waving up and down just like normal as it goes through. So it's only in this region of space where these two waves are interacting that they're canceling out. And same thing over here for constructive. It's only this region in space where they're adding together. If they were to continue on their way, maybe in opposite directions, they'd just be the same wave going past, going sort of their own way in their own direction. So with this process of constructive and deconstructive interference, what we can get is a phenomenon known as a standing wave. So a standing wave looks something like this, where we have the two waves that are kind of, have a boundary this way and a boundary that way. So it's the waves going this way and that way, waves going opposite directions always. This can even be one wave going this way and then reflecting back on itself. To create these types of patterns with different ways that waves are reflected. So if we start at time equals 0, we have this wave going this way, this one going that way, and we get this resultant here where they're adding together. Then at a quarter of the period of the wave, if we let time go, they'd completely cancel out. At half the period, instead of our middle being down, it's now up in the positive direction, and our beginning and end are now in the negative direction as opposed to in the positive where they started. 3/4 period, they've canceled out again, and now we're back to where we started once one period has elapsed. And so what you can see is that, say, if we take just this beginning, it essentially goes down to 0, down to negative, back to 0, and back up. So it's just doing this the whole time, and each part of that wave is simply just moving straight up and down that time. So it appears as if this wave is standing still, and it's just moving up. It doesn't appear to have any velocity in either the left or right direction because of the way this interference is occurring. And that essentially is a standing wave. It doesn't look like it's moving because of the interference pattern. It looks like it's just sort of vibrating up and down. And there's a couple important features that we want to point out with standing waves. So let's take the example of having, say, string attached at two ends here. And if we just pluck this string right in the middle, we have the most motion here, and since we're attached at either end, no motion at that point. Any point in a standing wave where you have no motion, it's called a node, and any time where you have the most motion, it's called an antinode, and then this whole thing is a loop. So you notice kind of the biggest wave we can fit in here is actually half of the total wavelength, because it's just the up part, and then the down part of the wave would be here, just the crest, and then the trough would continue, hypothetically out that direction. And so because we know this length, and we know that this is half of a full wavelength, we can actually figure out the frequency of that wave and the wavelength of that wave. So the total wavelength would be 2L, and because frequency would be velocity divided by wavelength, it's velocity divided by 2L. Now, if we take this picture and we kind of carry it out a little bit, there's actually multiple ways we could create a standing wave on this length here. Those look like this, where I can also have, the fixed points here, but also a node in the middle and two vibrating antinodes here going up and down. This is my three nodes, my two antinodes. I could have nodes here, here, and then two in the middle, and still fit that wave in there and have my three antinodes. And the names we give these things, the longest possible wavelength we can create is our fundamental frequency, what we call our fundamental frequency. And then everything after that is first overtone, second overtone, so on and so forth. The other word that we have for those instead of overtone is harmonic. It can kind of be used in conjunction with that. Our fundamental frequency is our first harmonic, second harmonic, third harmonic, and so on and so forth. And so that's kind of the language that we use there. And so each time we go to the next overtone, we're essentially adding a node. So here we have 3 nodes, 4 nodes. The third overtone would have 5, 6, so on and so forth. And we would just kind of continue that pattern. And you can see the pattern in the frequencies sort of continues as well. The pattern is essentially however many antinodes you have divided by 2. So 1 over 2, 2 antinodes, so 2 over 2, just 2's cancel out. 3 antinodes, so 3 over 2L. If we go on, it'd be 4 over 2L or 2V over L, 5V over 2L, so on and so forth. And that pattern is going to continue, and that pattern is going to be very important to us a little bit later. The next thing that can happen when we're talking about these waves is the phenomenon of a beat. A beat frequency is going to come about when we have 2 waves of similar frequencies. So let's maybe say a frequency of 440 hertz and a frequency of 441 hertz. Let's say this is music, both being played at the same time. So 440 hertz tone, 441 hertz tone, both being played at the same time. When that happens, it kind of looks like this. So we have our first frequency, our second frequency, those 2 waves, and you can kind of see that the pattern that's created, the resultant, is we get sort of loud, if this were sound, loud, quiet, and sort of that alternating pattern. And a beat frequency is how many times per second, right? Frequency is cycles per second. How many times per second do we get that alternating loud, quiet, or constructive, destructive type of interference? Beat frequencies are really easy to find. If I play a 440 hertz and a 441 hertz tone, my beat frequency is simply the difference between the 2 tones, 1 hertz. So whatever we do, you can calculate the beat frequency just by looking at the difference in the 2 tones. Whatever the difference is, that's your beat frequency.